Hello everybody, welcome back to the Valence Swabian. In today's video, we're gonna be solving the problem number 12, which is a very interesting one. We have like an arrangement of three particles and a little bit of geometry is going to be applied on this problem. So let's jump right in. Three positive particles of equal charge plus 17 microcoulomb are located at the corners of a equilateral triangle of size 15 centimeters. Calculate the magnitude and direction of the net force on each particle due to the other two. So I put some letters. You got particle A, B, and C. And since all of them has the same magnitude, 17 microcoulomb, and the distance between them is 15 centimeters, they all are going to be experiencing the same net force due to the others. So the final answer is just 1, and it's going to be the same for all of them. So let's start by analyzing the particle C right over here. Particle C are going to be feeling particle A pushing it away, same as particle B, since they have the same magnitude and they're all positive, meaning they will reject each other. So this is gonna be force net, and this is also force net. So force net is gonna be equals to the Coulomb's constant times the product between particle 1 and particle 2, could be C and B or A and C, whatever, they all have the same magnitude, over the distance square, and that is 8.9 times 10 to the 9, 17 times 10 to the minus 6 coulombs square over meters. We have to convert centimeters to meters and microcoulombs to coulombs, and that gives us 114.31 newtons. Now we know they have an angle. This net force has a specific direction. So what is the angle for an equilateral triangle? This is 60 degrees, right? So that's what they have here, 60 degrees. So this force has two components, the one going in the x direction and the one going in the y direction. So the one going in the x direction is going to be equals to force net, because we are analyzing half of this picture. So the angle 60 is going to be divided in half, which is 30. So right here we got 30 degrees, and we can and now we can apply trigonometry. So the x component is going to be the net force times sine of 30 degrees. But at the same time, this other force has the same equal force, the same magnitude, but with different direction, which means that they will cancel out. Particle C is not going to feel any force in the x direction because they will cancel out. Instead, the particle C is going to be feeling twice as the y component from this net force. So the y component is going to be F net times cosine of 30 degrees. And as you can see, these two components go in the same direction. So this particle C will experience twice as the y component from this net force. And that is 114.31 times 0.86, 98.99. So this is just one component, but since we have two of them, the result force is gonna be twice as the y component, which is 197.99 newtons. So look how we figured it out just by using basic trigonometry and geometry. So this final force, 197.99 newtons, is gonna be the same force that particle A will experience, particle B will experience too, since this is a symmetrical system. However, this problem is also interested in finding the direction of each particle. So we already know the magnitude and the direction for the particle C, which is called vertical. What about particle A and B? What is their direction? This is a triangle, right? So here you have an angle of 60 degrees, and the final component will follow the line dividing these 60 degrees in half. You remember that? Right here, you see it? It's the same, but it's just like another perspective. So just let me draw some lines. And this is basically, this is 30 degrees, right? This is 30 degrees. And this is also 30 degrees, right? And the opposite angle is also going to have the same 30 degrees, because these have 30, so these also have 30. 30 degrees following the x-axis. Same for particle B. So since this is 30 degrees, so this is also 30 degrees. And there you go. You got the directions for each particle and the magnitude, which is 197.99 newtons. See you guys in the next video. Bye bye.